Michael Faraday was one of the greatest scientists in history. It was his research that established the concept of the electromagnetic field. This video is a discussion of Faraday's paradox, which resulted from one of Faraday's experiments. I will demonstrate an example of how the paradox can be resolved. Motivated by an experiment in 1824 by French physicist François Arago, Faraday in 1831 devised the first electric generator, now known as Faraday's disk. The magnet in Faraday's machine created a magnetic field through the disk. When the crank was turned, the disk cut through the magnetic field and a current was induced radially outward from the center of the disk to the rim. However, when Faraday reversed the experiment, turning the magnet but leaving the disk motionless, he observed no current. This was surprising to him because he reasoned that any relative motion between the two parts should create a current in the disk. This is the first part of what is now known as Faraday's paradox. Furthermore, when Faraday turned the magnet and the disk together, he observed a current. This was again surprising because he expected zero current since there was no relative motion between the two parts. This is the second part of what is now known as Faraday's paradox. I will now demonstrate a simple method to resolve the paradox. This is my model of Faraday's disk. Instead of a hand crank, I use a small electric motor to drive it so that I can have a uniform speed. And it consists of a copper disc, 6 inches in diameter, and an alnico magnet, which is similar to this one. It's got a metal case on the outside of it, which will come in handy later. This is case 1, where the magnet is not moving and the disk is moving. I measure negative 0.3 millivolts. This is case 2, where the magnet is spinning and the disk is not spinning. I get 0 volts when I measure at the center of the disk. In case 2, the magnet was moving and the disk was not moving. So there was relative motion between the two, yet we measured 0 volts. This is the first part of Faraday's paradox. This is case 3, where the magnet is moving and the disk is moving. If I measure in here at the center of this disk, I get negative 0.3 millivolts. And in case 3, the magnet was moving and the disk was moving together, so there was no relative motion between them. And we would have expected to see 0 volts, but we measured a voltage. That's the second part of Faraday's paradox. As many others have pointed out, the paradox is caused by the measuring circuit. When you measure like this last portion here, the probe, is under the influence of the magnetic field, which is moving when the magnet is moving. So there's an induced EMF in this part of the circuit. So to get around that, we'll change how we're measuring to this point. Instead of reaching in there, we're going to come over here to the axle, which is electrically connected to the center of the copper disc. And then we'll go out here and measure at the outer edge of the magnet case. Now this whole magnet case is moving at the same speed as the magnet. So there's no magnetic field that's inducing an EMF in the magnet case. So now our circuit has no induced EMF from the rotating magnetic field, and we're still getting a connection to the center of the disk if we measure out here. Now that we know how to eliminate the influence of the rotating magnetic field on the measuring circuit, I will remeasure the voltages produced by the Faraday disk generator for the 3 cases. This is case 1, where the magnet is not moving and the disk is moving. When I measured this before, I got negative 0.3 millivolts at the center of the disk. If I measure out here at the magnet case, I still get negative 0.3 millivolts. This is case 2, where the magnet is spinning and the disk is not spinning. When I measured this before, I got 0 volts at the center of the disk. Also get 0 volts at the axle. But at the outside diameter of this magnet case, 0.3 millivolts. This is case 3, where the disc and the magnet are moving together. When I measured this before at the center of the disc, I got negative 0.3 millivolts. If I measured over here at the axle, I would get the same thing. If, however, I measured at the outside of this magnet case, I get 0. So by rerouting the measuring circuit through a conductive disc co-rotating with the magnet, the measured voltages for the 3 cases reflect what we expect them to be, and the paradox is resolved.